Okay, so after covering independent events, we're ready to talk about some properties of independence. And they can be really handy, as you will see. And a lot of ways, in many cases, we have been using that unconsciously already. So now we're good to go over them formally. Okay, so first one, A and B are independent, then B and A are independent. Okay, not surprisingly, okay, no order. It doesn't really matter about which order you're going. If A and B are independent, then B and A are independent. The second one is quite interesting here. If A and B complement are independent, then also A complement and B complement. Okay, so we know that if A and B complement are independent, meaning that B complement doesn't affect us, our understanding about A, then naturally we'll imagine that B complement wouldn't affect our understanding of A complement either, because it's like A itself, A or A complement does not really matter in terms of B, okay, B complement as well. So that's a good thing to keep in mind. And if you want to formally show it, check out the textbook or try it yourself, just to follow the definition carefully, okay? The third one here is very important, and I will just highlight it. Independent is not disjoint. Okay, so independent, as we have been talking about the definition, is just saying that the information about one event does not affect the does not affect the other event at all. Okay, when they're independent. Disjoint, if you remember what we talked about before, is that disjoint events just saying that they cannot happen at the same time. Okay, so mathematically, independent is what we have just covered. Okay. Like the joint probability of A and B is the product of the marginal. Okay. Disjoint, so that's independent. Disjoint, if you remember, if event A and event B are disjoint, then their probability of the joint probability, I should say, is 0. Okay, meaning that A intercept with B is the empty set. Okay, so mathematically now you can see that they're really talking about two different things. But I would just say that it's very easy to use these two terms interchangeably. Okay, but now you can see that they're really not about the same thing at all. And another thing I would just mention, just as an example, let's just say independent. So let's just say in what situation you might have independent events that they're also disjoint. Okay, let's just say we're talking about tossing a coin twice. Okay, let's just say the outcome of the first one is tail. The other one is also tail. Okay, so when you look at outcome like this, and we know that, well, they're independent from each other. Okay, so that's what we mean by independent. And we know that you get this happen is 1/4, right? Because it's 1/2 to the power of 2. But as you can see here, they are not disjoint, okay? Because they could happen at the same time, all right? So I just wanted to use this example together with this mathematical definition here to highlight that independent is not disjoint. Okay, disjoint is not independent. So when we are thinking about those concepts, we want to make sure that we're following their definition carefully, as well as in applications, we want to make sure that we're doing everything correct. All right, and then from that, we have another property, what we call, or definition, more appropriately, a definition for mutually independent events. Okay, so when you have 3 events, A, B, C, they're mutually independent if, so the first condition here is saying that pairwise, each of them, okay, each pair, A and B, B and C, A and C, they are all independent from each other. Okay, so that's what we have, this 3 equations here. But also it needs to have all of the events A and B and C, they together are independent from each other. Okay, so what that means is that if I'm chaining here, right, the intersection A and B and C, then it is the same as the product of the 3 over here. Okay, so they are mutually independent if they are not only pairwise independent, like what we're showing in item 1, also that they are independent from each other when you're thinking about all of them jointly. Okay, so this is what we mean by mutually independent. So of course, it could be that only one holds, okay, meaning that the first three items that first three equations that we're seeing here, each pair, they're independent, then we call them pairwise independent. But if they're not, as you can see, if they're not jointly independent from each other, we only call them pairwise, but not mutually independent. Okay, so you can also understand that if three events are mutually independent, then they must be pairwise independent. Okay, however, if A, B, C are pairwise independent, it's not necessary that they are mutually independent. Okay, so you can think of pairwise as a subset. Okay, if we use that kind of notation, is a subset of mutually independent if we're thinking about those events here. All right, let's give you an example of events could be pairwise independent, but not necessarily mutually independent. Here, we're rolling two fair six-sided dice, okay? There are three events here, A, B, C, and as you can see from the title of this slide, we're gonna show that they're pairwise independent, but not mutually independent. So to get started doing that, let's maybe first think about the event, the probability of each of the event here, okay, just to make sure. So probability of A, okay, so sum is 7, okay, so we know that we're doing two fair six-sided dice, so the total number of equally likely outcomes is 6 times 6, okay, so it's 36. The numerator, as we know now, we have to actually list all of the possible outcomes, right? So we're gonna 1, 6, okay, 2, 5, okay, 3, 4, okay, but also you can have 4, 3, 5, 2, and then 6, 1. Okay, so if we count, the number of outcomes here is 6. Okay, so we know that the probability of A is 1 over 6. All right, probability of B here, the first row is 4. Okay, it doesn't matter about the second row, and we know that it's a fair six-sided die, so it's going to be 1 over 6. Okay, similarly, probability of C is going to be 1 over 6 because we're only looking at the second row being 3. All right, so with all of this in mind, okay, let's check one by one. The first one, as we know, in order to check their independence, is looking at the pair of A and B. Okay, so the A and B, as we know, if we want to have A and B happen at the same time, this row, the two rows will have to be 4 and 3. Okay, meaning that the first one is 4. Okay, that is like event B, and then if the sum has to be 7, then the second row will have to be 3. Okay, so this pair to happen, we know that it's going to be 1 over 6 times 1 over 6, right, is 1 over 36. Okay, that's the left-hand side. And the right-hand side, we know that we just did it before. We label those values up there. So we know that if we check this, we're able to show that, well, indeed, this pair of two, A and B, they are indeed independent. Okay, so let's keep that in mind. All right, and for B and C, okay, actually, for B and C to happen, now we know this two rows also will just have to be 1 over 4 and 3 in that order. So as we will show without showing, but you know that it's going to be 1 over 36 on the left hand side and also equals to the product of the two. If we keep going, A and C, well, A and C as well, it will have to be that particular sequence of 4 and 3 in that order when we're doing the die roll. So that again, not surprisingly, shows that they are true. Okay, so we have shown this and this and this. Okay, so that's only showing that they're pairwise independent. Okay, how about whether they're mutually independent, right? So that is the case where we have to show the joint of A and B and C is the product of the 3. Interestingly, here we know that the right-hand side, right, is 1 over 6 for each. Okay, but if you look at the joint of A and B and C, it turns out that the only way that this could happen is 4 and 3 in that order again. Okay, so we know that, well, the left-hand side will actually have to be 1 over 36, and apparently it does not equal to 1 over 6 times 1 over 6 and times 1 over 6 again. Okay, so this is a example to show that 3 events, they could be pairwise independent, but not necessarily mutually independent. Okay, so again, if we go back to the definition from the previous slide, we know that mutually independent events means that they're definitely pairwise independent because it's part as one of the two conditions. But then if they're pairwise independent, it's not necessary that they're mutually independent, just like what we have shown in that example. Okay, so hopefully this gives you a good point to think about how to understand the difference between pairwise independence and the mutual independence when you're working with 3 events. Okay, so that's for 3 events, and we actually also can generalize things to multiple events. Once we do that, we actually just focus on talking about whether they're independent or not. In this case, okay, so we use this term, okay, when we're talking about more than like a larger number of events. We call them, if they're independent, only if the joint probability of all of them is the product of all of the marginal. Okay, so when we're talking about this, we don't really differentiate pairwise or mutually anymore. We're now just saying that when we are talking about n different events are independent from each other, then if you can see it here, right? If you pick any r out of this n, you can always show that the joint is the product of the marginal. Okay, so if you can satisfy this, then we're saying that a1 through an, they are independent from each other. Okay, so again, look here, we're selecting any of the r. Okay, it could be 2, it could be 3. So if you can satisfy for any r that you're picking here, then we know that a1 to an, they're independent from each other. Okay, so lastly, just to keep in mind, the key to compute the probability of independent events is just to multiply the probability of the individual events. Okay, so again, we have been doing that consciously, unconsciously in the past. And now I hope with this definition formally being introduced, and then we see some examples, we know that why that is the case, and then why we're able to take in the product of the marginal in order to get the probability of the joint. Okay, so lastly, let's end with an example. A fair coin is tossed 5 times. Okay, compute the probability of 5 tails. So without thinking about any independence, like all of the events, for example, like the expression that we show at the top, we know that, well, it's a fair coin, right? And it's tossed 5 times. Each time to get a tail is 1/2, and they're independent, so you're taking the product of all of them. So it's going to be 1/2 to the power of 5. Okay, and more formally, we can define T1, T2 until T5 to be the outcome of each, right? Of each toss, and then like T1 is the first outcome as tail, T2, etc., etc. So we are trying to pretty much using this result here. Okay, so if we're trying to get the joint probability of all of them are tail because they're independent, it's the same as multiplying the marginal probability of each of them being a tail. So that also gives us, like what we talked about, 1/2 to the power of 5.